So let's get started. So this is our Tidal Flat seminar series. It is part of the Office of Naval Research funded project, Littoral Mudflats and Shorelines, Soil, Sea, Ice, and Air, and benthic life interaction. This project aims to develop a fundamental and comprehensive understanding of the geomechanics of littoral mudflats and shorelines towards reliable prediction of geomorphodynamics, trafficability, and navigation from satellite images and geoacoustic surveying. I'm really excited to have an international speaker here today on site. So thank you so much, Barret, for visiting us. We're excited to have you here. And just a little bit background about Barret. So Dr. Barret Kurylyk holds the Canada Research Chair in Coastal Water Resources at Dalhousie University in Halifax, Nova Scotia. This research program integrates field and model-based investigations with a topical focus on groundwater dynamics and a geographical focus on coastal and Arctic regions. He has received early career research awards from several organizations, including the Geological Society of America and the American Geophysical Union. He's currently past president of the Canadian Geophysical Union Hydrology Section and second vice chair of the Geological Society of America Hydrogeology Division. We are in particular excited to have you here because I really appreciate the field you're in. I think there's very few people who do such cool work as you do in this field. And we also know that Nova Scotia has some really exciting and big tidal flats. So thank you again for being here and giving us this lecture.
Okay, thank you very much, Nina. Hopefully everyone can hear me online. It's great to be here. Thank you for the introduction. Nice to be back in Gainesville. So I want to talk about maybe the first 3/4 of my talk. I think I'm going to stand up. I'm just used to doing that. I'll probably sit down eventually. But 3/4 I talk on kind of hydrogeology, coastal hydrogeology stuff, and then I'll finish with thinking about connecting some of that to coastal geotechnics. And all in this tidal-dominated area of the Bay of Fundy. So I should acknowledge a few people. Nicole Rue, who's in the blue shirt here, she's a present PhD student of mine, and Hayden's a former PhD student of mine. A lot of this is their work, and then Greg Lake's a colleague in my department who Nina knows. And then Aaron and Joe are former postdocs from my lab who did a bunch of stuff. So really presenting on behalf of them. I'm not sure how much people know about Canadian geography, except that we're big, but we have about 5 times longer coastline than any other country in the world. And it's a pretty dynamic coastline. We have the Arctic coast, of course, which is permafrost. And then our Atlantic and Pacific coasts are seasonally frozen. So all of our coastlines impacted by freeze thaw. And then on top of this kind of ground freeze thaw dynamics, we have sea ice melting and freezing, and that is changing. And through time, less sea ice cover, shorter cover, less extensive cover in space. And so we have changes to like the wave forcing on our coastline as well. So there's a lot of concern about changes to the coast, and especially in sort of northeastern Canada or southeastern where I live. In the Maritimes. So Newfoundland, you see is sort of the bigger island there, and then PEI, Nova Scotia, New Brunswick. Collectively, those are 4 Atlantic Canadian provinces. And if you just look at these 3 here, they're called the Maritimes, so without Newfoundland. And so there's all kinds of interest in the Maritimes on kind of changing coasts and coastal flooding, coastal erosion, sea level rise, coastal weakening, but not a lot of concern about the impacts of the changing coast on coastal aquifers, which is kind of where I'm focused in my work. So this is from Claire Robinson, who's a good friend and colleague of mine at Western University, from a review paper she wrote. The light gray here is supposed to be fresh groundwater, and it's coming out to the coast through this freshwater tube, it's called. Underneath the tube, we have this salt wedge, which is a zone of dense saline groundwater. That's not saltwater intrusion unless the wedge starts moving, and then it is intrusion. And then we have up here something called the upper saline plume, which is like a tide and wave dominated circulation zone that's brackish. And we all know what surface estuaries are. A lot of people refer then to this deeper zone of groundwater mixing of fresh and salt water called the subterranean estuary. So there's exchange of solutes and heat and just basically a biogeochemistry hotspot. And then we have the upper saline plume, which I already mentioned, just to draw your attention to that, because I'll come back to that. So anything, I should say, anything that's changing in terms of the coastal zone processes, so marine forcing like sea level rise, storm surges, waves, tides, all those processes influence what's going on in the subterranean estuary on different time scales, whether those are through tidal cycles or through millennia. Another thing connecting coastal zone change and groundwater is basically coastal zone flooding and vertical saltwater intrusions. This is Julia, who finished her PhD with me this spring. And she did work on looking at changes to foredunes and when they're eroded or moved back, you have more extensive zones for coastal flooding. And then that pooled seawater can then basically vertically infiltrate down into coastal aquifers. And it moves in these salt fingers, which are basically density dependent flow cells. And they can, generate in a few hours, but take up to decades to flush out depending on the aquifer properties. All right, so this is a map of the groundwater use throughout Canada. About a third of our country drinks groundwater, and that ratio is much higher in the Maritimes, so a very rural area. People don't have centralized water in large part. So all of the province I grew up in, PEI, is groundwater dependent. About half of Nova Scotia is, and almost 3/4 of New Brunswick. So in this area where we're experiencing a lot of coastal zone change, people rely on coastal aquifers, and so changes to coastal aquifers imposed by oceanic changes or shoreline changes really could have profound implications for communities, and already are. So this gets us to the Bay of Fundy, which is, here basically between Nova Scotia and New Brunswick. These are maybe I'll look at this time lapse here. So you see the tides go up and down. This is really typical for these communities. They have really high wharfs. And at low tide, often the boats can't even connect to the ocean. So the communities run on the tidal clock, basically. Everything works in terms of the economic activity around the tides. I have family that fish on the Bay of Fundy, and their lives, they get up at 3 a.m. one day, they might not get up till 8 a.m. a few days later based on tide times. And it's just, really high range. You can see these tidal range ISO lines here. It gets up to about 16 to 17 meters at high tide in this, what's called a minus basin. So 55 feet tidal range. So the highest in the world, according to Bay of Fundy people. There's a couple other places that are really similar though. So a couple things drive these really high tides. One of which is that the period of the basin has very similar time to the M2 tidal constituent, so there's tidal resonance, and you also get some funneling effects as you move up into the basin, which is why we have higher tides up here. So when the Acadians were the dominant culture, I guess, in terms of European culture in Nova Scotia, they built these dikes everywhere and basically reclaimed these tidal wetlands because they're really rich agricultural fields. And eventually, I guess, British took over and relocated many of the Acadians all the way down to Louisiana. But those dikes still persist for hundreds of years, and they're not adequate for present sea levels or changing sea levels. And there's already a lot of concern about Nova Scotia becoming island, especially here where it's all low lying across the Chignecto isthmus or peninsula isthmus. So it's a really hot topic politically now in Canada. The federal government's on the hook for a bunch of money to build up these dikes. Provincial governments are fighting New Brunswick and Nova Scotia over who owes the money for the provincial commitments, and then municipalities are footing the bill locally for some work. There's a really cool,
Can I ask, just out of curiosity, what are the bathymetries in the bay? I mean, what fraction of the bathy depth is the tidal range?
I do not know that offhand, Pete. I should know that. I know, like through here, the low tide goes really far out,
Okay.
but I think it's probably pretty deep through here.
Yeah, but that upper part, exposure, huh?
Yeah, positive exposure. So yeah, Garret, who used to be at oceanography in my university at Dalhousie, wrote a cool paper on sort of the physics of the Bay of Fundy and nature, if anyone's interested. And these Desblanc and Bosman wrote really detailed papers. They're at a local university. What I think is cool about the Bay of Fundy is the actual tidal range, if you add all those constituents together, so high that some of those lower impact constituents become really important, like this 18-year period signal. Where the increase right now in the high tide mark due to this 18 period signal is actually, the rate is higher than sea level rise rate. So obviously to get to the top of that signal and go back down, but sometimes these low period constituents become really important thinking about tidal flooding. and high water mark. So really huge tidal prism. And let's see if I probably didn't enable my videos here. Let me check if I did. And because of the high tidal range, there's tidal bores in a lot of these rivers. I don't think this is probably did something wrong. It's not that impressive a video, but anyway, the tidal high tides come up as these bores in most of the rivers that flow into the Bay of Fundy. So like a really sharp front. Physics of those are interesting in and of themselves. And in the city of St. John in New Brunswick, the mouth of the St. John River, which is a really big river, not like the Mississippi, but pretty big, comes down and it falls in St. John, but the fall direction flips at high tide. So they pitch this reversing falls as why you should go there, I guess. So we've been working with Kate Sharon, who's a really cool environmental social scientist at Dalhousie. That's taught me a lot about how people think, because I never understood people. I still don't. But there's a lot of ecosystem services that dikelands provide and also tidal wetlands provide if the dikes are removed. And so there's a lot of things that could happen in terms of dike decisions. They could move them back, they could build them up, or they could knock them out entirely and just let nature or the bay reclaim the tidal wetlands. And so people think very strongly about what's the right approach in different areas. There's indigenous perspectives in the area. There's people who, whole businesses run on dikelands. There's people who are really big on using the dikelands for recreation. And in particular, a lot of communities need major trails that people run are through the dikes. So anyway, can't digest this slide, but the point is there's a lot of complex stakeholders at play and ecosystem services, and all this is trying to get our heads around what are the right approaches in different areas for what to do with the dikes. Which gets me to the town of Wolfville, which Nina's probably been in a bunch. It's a really pretty town on the Minas Basin, which is sort of the upper Bay of Fundy. There's a little university there called Acadia University, which has been around a long time. So this is where Nicole did her master's. So this is Nicole during her master's, and she is now more mature as a PhD student. And this is her conceptual model. This is a dike system. And then here's a tide going up and down the bay. This is protecting agricultural land. What we don't know, let me switch back to this, is things like how big this upper saline plume that I talked about earlier is, because the upper saline plume is driven by tides and sort of maintained by tides. And so with really high tides, you'd think they would be larger, but nobody knows how big they are. And we thought this was cool because when people think about saltwater intrusion, they think about this deeper salt wedge moving, but not about maybe the upper saline plume moving, which is really relevant in Wolfville because they're pumping from the groundwater system very close to the dike. In fact, they're pumping it sometimes below sea level, the groundwater level. And then we're also interested in overtopping, or Nicole did a lot of work on overtopping of the dikes and infiltration of seawater in behind them, thinking about how that might change with or without the dike in place. There's Nicole and Ryan, who also did a master's with me. They're putting out a tidal station there. It's kind of a miserable place to work. We probably could use that hovercraft. Here they are putting in more piezometers. We got pretty good with our little backpack drill down maybe 5 or 6 meters there. Here's the dike here. And you can see right landward of the dike, there's pretty critical infrastructure. So for example, that's their wastewater treatment ponds right there. And this is true for much of the town. So we put out tidal station, wave buoy. It's pretty low wave energy there, but we had it in place. We put in CDT loggers in our piezometers and also had a deeper well and did a bunch of geophysical and drone-based surveys. So here's some pretty cool data, I think, from Nicole's master's thesis. Maybe I will sit down, give myself a back problem. This light blue here is the surface water tide. So really textbook, beautiful sort of M2 tidal constituent or tidal signal with this lower spring neap signal in the background. We don't quite capture the low tide here because our station wasn't out far enough, but we got a pretty good representation of the tides. So that's the surface water. And then blue here is the groundwater. And then the 2 orange lines correspond to the right axis and show the EC values. They're basically a representation of salinity. So the bay is the upper EC line. That's pretty constant at around 45,000 microsiemens or 45 millisiemens per centimeter. And then the groundwater, I should say, here's our deep well here in this black signal or symbol. Here's our tidal station here. And so this here well is about 100 meters inland and 70 meters deep, so pretty deep, pretty disconnected from the surface water system in some ways. And if you look over here, just zoom in for a couple of days so you can see things better. The light blue is the groundwater head, sorry, the surface water head or the tidal series in the bay, and the dark blue is the groundwater signal in that deep well. That might not look very impressive. That's a super high groundwater tidal amplitude, like 1.5 meters. And considering it's 100 meters inland and 70 meters deep, really wouldn't expect to see that kind of tidal range. But the EC is not changing. So this is not like surface water, Bay of Fundy water going into the groundwater system and coming back, or you'd see this in the EC signal. It's like a pressure pulse or celerity effect going in. It's hydraulic diffusion effectively. If you do a fast Fourier transform or any other way to convert to frequency domain, look at the spectral density, you can see the M2 signal dominates, and that's true in both the dark blue and light blue, the groundwater and the surface water, and some of these other constituents show up. What I thought was cool that Nicole did was she put out her geophysical transect or station right here. So basically you have a current, like a loop that you put a current through, and you turn the current on and off in the loop, and it generates electromagnetic field. And then you measure how the ground responds to that electromagnetic field. And then you can do inversion and back out the electrical properties of the ground, which are really important way to discriminate salt water and fresh water underneath the land surface, because they have different electrical properties. And so we did time-lapse measurements with our system. You can see these are just the time shown here when we did the different measurements. So red is high tide, blue is low tide. And here are the resistivity measurements versus depth. So this is like 1 over electrical conductivity. So low resistivity is salt water, high resistivity is more fresh water. And there's geology effects here as well, not just salinity. But what I thought is really cool is you don't see any changes over the tidal signal in the upper 20 meters, and you see really profound changes at depth. And as you would expect, so the red series is sort of like the saltiest one, shows up as the lowest resistivity or highest EC, the saltiest groundwater. So this shows that there's crazy amount of actual advective mixing, which we don't pick up in the well because it's a bit further inland and also deeper. But we see this really obvious, huge amount of mixing over a single tidal cycle at crazy depth. So what's happening is, I don't know how much people know about hydrogeological properties, but the upper 20 meters is probably an unconfined aquifer where there's a lot of storage, specific yield storage like porosity, whereas the deeper one would be a confined aquifer where you have very little storativity, so signals can go in much further through fractured rock likely. So we think this is the upper saline plume basically, which is quite large compared to anything that's been mapped elsewhere. So Nicole did some modeling of this in hydrogeosphere. I don't know how many people have ever seen or heard of hydrogeosphere, but basically it's a University of Waterloo spinoff through the company Aquanti. And it does surface water modeling using the wave equation, and it does groundwater flow modeling with the Richards equation, and the domains are integrated to talk to each other. So basically, Nicole put like ocean tides on this orange area, which was our surface water boundary, and a salinity of 1, relative concentration of 1, so ocean salinity, and looked at how tides drive that upper saline plume, but also what happens if you put sea level rise on the tides, does the plume move? And also when you put sea level rise with storm surge, how much it takes for the surface water to go over the dike, and then how long does it take to infiltrate and then flush out? So all this sort of looking at the role of surges, tides, and sea level rise on the groundwater system, basically. So here's a hydrogeosphere profile view where the color just shows the salinity, relative concentrations. Red is ocean water, blue is fresh water. So here's our bay here. And we could calibrate to this one head measurement we had at depth, which isn't a great calibration point. So you can see the simulated and observed head there. It's actually a lot of equifinality issues because you can change 2 properties that will give you the same head response, the hydraulic conductivity and the storage coefficient. But what really helped us was we knew there was no high salinity water here because our EC logger told us there wasn't. And most of the combinations that we could get to match this tidal signal caused the plume or the wedge to come pretty far inland. So it turned out to be really helpful having basically a data point that we knew was fresh. And here's some of the upper saline plume in white. This is kind of after after steady state conditions for present sea level, and then she turned the tide off and watched how long it took for the plume to disappear, but also put sea level rise on and looked at how the plume expanded. There's kind of a lot going on here, but the key point is the upper saline plume expands and moves landward in response to sea level rise. And we think this is actually pretty important in this area because they're only monitoring the deeper salt wedge, but actually I think becoming vulnerable to actually contaminating their groundwater through upper saline plume movement. But the other thing she did, as I mentioned, was look at overtopping of the dikes. So this is basically the whole domain shown in these panels up here. And then if you zoom in just the upper few meters, so that the black dashed line or black solid lines here show, sorry, I've got a bit of a lag, but show the zoomed in down here. So these are basically showing in behind the dike. And she just looked at the effect of what role does the tide play in actually limiting or enhancing the exchange of groundwater and saltwater in terms of the flushing mechanism. So once the dike is overtopped and you get salty water infiltrating down into the soil, that has to eventually be flushed by fresh rainfall or snowmelt. And the rate at which it is flushed depends on the tidal dynamics, depends on the dike and a lot of other things. And so she just turned things off and on in the model and showed some of these interactions. All right, so that's work at Wolfville. I wanted to also talk about work in Truro. So this is the Salmon River, which is a macro tidal river at this location. It flows into the Minas Basin, the upper Bay of Fundy. This is the town of Truro here. Kind of an agricultural area. It has a little Dalhousie University campus there. Basically, your ag schools in Truro. And you can see this is just across the river from Truro. This is all agricultural land. And if you zoom in carefully with your eyes, I guess you could probably see this dike that runs along here. And also you can see one on the other side. So this river floods all the time, or it used to, because there's no floodplain. It's just dike on both sides. So when you have a lot of flow going through, the water level goes up and over the dikes. And so it floods into the town way too often, or it was. And so a few years ago, they decided to try to move these dikes back to see what would happen to the river, to the estuary. And so basically this whole area, which is an agricultural area, would be reclaimed as a floodplain, which would hopefully limit the high water levels and keep the town from flooding. So this is work that Hayden Tackley did. Hayden just finished his PhD this summer. And this is a little invited review he wrote for this Wires Water Journal. He's interested in general on the impacts of changes to estuaries. And thinking about estuary as this basically short circuit route for salt water to go up into landscapes and flood radially out from the estuary into the soils and basically salinize the soil and underlying groundwater, which he's showing here. And he did a little bit of a global analysis of different parts of the world where this might be important. But that's why we basically did almost all the work, just field work in Truro along the Salmon River. Here's Hayden. Here's me standing next to one of the dikes after they moved out a big chunk of it, so knocked it out. They call it dike breaching. You can see the tidal signals here coming up very spiky, like a tidal bore. That's in the surface water in blue, and then you see these signals also very apparent in the groundwater system and the different piezometers we installed everywhere. It's actually kind of an interesting site because there's the tidal river and a tidal stream. And so you have these, they come perpendicular to each other. And so you get this orthogonal tidal signal transfer into the groundwater system that messes up a lot of the physics that people usually use or the equations people use. Why we like this site is because it only floods every spring high tide. So we know exactly when it's going to flood. We can instrument it before and after a flood. It's kind of like this nice engineered analog of tidal flooding, which is supposed to increase in the future under sea level rise scenarios. And in theory, a lot of places in the world are going to experience tidal inundation regularly, and that can force, migration from low elevation coastal zones, especially a lot of small island developing states. So here's some of the piezometers put in. We did some geophysics and a whole bunch of LiDAR with our drone. We used this little backpack drill, which also worked really well in the nice soft sediment there. So this is the photo I showed you already. This is kind of a little bit the same, but looking over here is kind of what you see there. But this is after it started flooding. So that beautiful green agricultural landscape is now a sort of brown, muddy tidal wetland. And this is, I think in the fall of 2021 was when the dike was knocked out. So this is in the first few months. And so the site's changing drastically. really profound erosion, channelization in places, really profound accretion or sedimentation in other places. And one of the things they did was also knock out this abato, which is like a one-way sluice valve at the mouth of this tidal stream. And that then all of a sudden there's a lot of high salinity water coming up into this creek as well. So here's Hayden at the abato. See, I think I have a figure here. So this is from our drone. You can see these old depressions in the agricultural landscape are preferentially being filled up with sediment. And this isn't in the lab. This is just in the field, just slice through it so we can get a photo. But this is what it looks like. These really distinct tidal rhythmites being laid down every spring high tide look like plywood. And in blue here, again, is the river. So it's a CDT in the river. CDT, LTC log for hydrogeologists anyway. So you see the tidal bore coming up. And then it's only flooding again at spring high tide. So maybe 2 or 3 times every fortnight in a row it'll flood. And in red here, you see the electrical conductivity. And so when it's flooding at the highest electrical conductivity. So it goes up to about 5,000 or so microsiemens per centimeter. So pretty low. I mean, that's much lower than the ocean, but certainly higher than you would want to drink. And we also put on these sort of equivalent loggers, just zip tied them to the outside of piezometers. So you can see when the flood water comes in the head that shows up. And again, the higher EC value. So the flood water, again, it's only flooding at the highest salinity, basically. Without going into a lot of details here, you can see the soil moisture profile shifting over time because basically when it's flooding every 2 weeks, it's getting wetter over time, the soil, because all that water is infiltrating, and that's really obvious in the soil moisture data. But it's also obvious in the, I'm not sure what I just did. No,
that's me.
It's also obvious in the geophysical data. Thanks. So this is what that little ski you see Hayden carrying is called the GEM 2, which is a really cool tool used by actually agricultural people. It's got multiple frequencies. So you can, when you do the inversion, you can get depth variation in resistivity or electrical conductivity. It's pretty cheap, and it's really fast to take data with in the field. So before the dike, this isn't very good inversion here, but you can see the blue upper meter or so. It's all freshwater. And then after the dike's breach, and it starts flooding. I think this was 6 months later. It's basically all salty down to a depth of 1 meter. So at least the saline plume's gone that far down. In general, we don't know very much about groundwater around estuaries. I showed you that schematic from Claire Robinson's paper that shows a wedge coming in along the marine coastline and the upper saline plume, but we don't know anything really about how groundwater looks around estuaries, just a couple studies in Australia on it. So Hayden, first of all, did some work in this suture model, which is a USGS groundwater model I've done a bunch of work with. Here's the river boundary condition here. You just let the river change its head and its salinity, basically. We had a bunch of measurements for calibration. And he wanted to look at the resultant plume. So these would be like the river here, the Salmon River. And wanted to look at the salinity around the river in the groundwater system and the role that things like sea level rise play on that, and also drought, because when you have drought, you have less fresh water in your estuary, you have more salt water coming up. So we did a lot of work in this lateral saltwater intrusion, which he, I guess, published the year after his other paper on the initial site changes. And then he did a bunch of work on vertical saltwater intrusion, which I think may be slightly more interesting. Here's the landscape again from above, and these areas, these old depressions where the sediment is being built up. So here's our original LiDAR flight at the bottom here, the elevation from it. And then after, I can't remember how long this was, I think about 2 years, the new LiDAR flight here. And you can see the orange is basically areas that are filled in with sediment. And if we do geophysics over those areas, they're also the areas that show sort of preferential saltwater intrusion. And that's repeated later on, it's just the plumes are extended further down. So we wanted, thinking about why this is, because there's kind of a few different mechanisms we thought about. So again, we have a bunch of data from piezometers to help calibrate a model. And Hayden did a lot of work in a vertical, like a 1D model with that Sutra USGS model I mentioned. Thinking about the role of the accreted sediment on saltwater intrusion, which has never actually really been studied to my knowledge before, and trying to think about why that preferential saltwater intrusion occurs. So here's some of the simulated salinity depth profiles in the upper 800 centimeters of the soil. So if we just put floodwater alone on the model, so basically let the flood come in, we know what the EC is, we know what the head is, we can see whether that's how far down that saline plume will go. And basically this here, horizontal scale shows a salinity, it's almost 0, so just need to note the difference in scale here. And we tried putting the sediment on, which the sediment itself can play a role because it caps precipitation from infiltrating down, because the sediment's really fine, low permeability. But that didn't really do anything in terms of matching our field data. Here's our field data here. We took a bunch of samples, but we were able to reproduce that general trend when we put, we started looking at applying the sediment as basically a salinity source in a boundary condition. Because the EC of the port water in the created sediment is actually much higher than the EC of the floodwater, which I think is just because the sediment's coming from much further down the river, but it's not something I'm an expert on. But the point is that here's this sort of conceptual model that we get this really low permeability material that caps the fresh recharge from coming in, but also is the source of high salinity or saline diffusion, if you will. And in some places where that was then removed through subsequent erosion, basically the saltwater plumes underneath it disappeared over time with geophysics, which suggests that that might be sort of like a landscape management technique that people could use. But just to make the point that the deposition of saline sediment accelerates vertical saltwater intrusion in these landscapes. All right, the third, where I got a bit of a lag here, Advocate Beach, which Nina did a bunch of work at, which was kind of the motivation. We were trying to find a site that had really basically the opposite of a tidal mudflat, a gravelly beach along the Bay of Fundy, which is pretty rare because most of the Bay of Fundy is tidal mudflats and low permeability, which doesn't facilitate as much groundwater surface water interaction or exchange. So yeah, Nina did some work with her former postdoc advisor, Alec Hay, on this, and then Alec had a subsequent PhD student, Tristan Guest, do some cool work on pore water pressure signals. And so that was kind of our motivation, I guess, getting started. So this is Aaron Mohammed, who's at Syracuse now. This was his postdoc. This is Sophia Stanek banging in with the slide hammer some of these dry point piezometers. We did some measurements offshore as well as on the shoreline. And basically our ultimate goal is to try to quantify the amount of groundwater coming from this beach, which you call submarine groundwater discharge. It's flowing directly to the marine environment through submarine pathways. And there's lots of different ways you can try to measure that. We use piezometers, seepage meters, which I'll show you in a moment, radium, and also radon over a couple summers. It's a little bit of a painful place to work because the beach, even though the beach is really steep, there's still a pretty large distance, like horizontally, between low tide and high tide. And so if we're trying to keep stationary locations to do our geochemistry work, we had to run really long hoses out to the beach and just run back and forth every day, which got really exhausting. But it was still a pretty fun site. Here's our offshore location here in the blue circle, so pretty close to the shoreline still. And this is where we put seepage meters. This is showing it at high tide, but these are not submerged at low tide. And we had a tidal logger here and a few piezometers on the beach, although a bunch of them turned out to be useless. One was useful. So Joe Tamborski, who was with me as a postdoc, he's at Old Dominion now. He did all the geochemistry for this because I'm not a geochemist. So we banged in these piezometers with a tractor over time just because there's this farmer slash fisherman who lived there who did everything for us with the boats and tractor. This is a seepage meter. I don't know if you have used these before, but basically like the top of a 45-gallon drum, and you cut them off and you can wiggle them down into sediment, and basically groundwater flows up into them, and it can only come out one point, this hose. And so if you measure the volume of groundwater that comes out of the hose, which you can collect in a bag, divide by the time, and then divide by the cross-sectional area of the seepage meter, you get the Darcy flux. Kind of painful way to get Darcy flux, to be honest, and plus it only gives you one measurement in space, and our K changes a lot, so the Darcy flux changes a lot. But we took 31 measurements with seepage meters, and I'll show you a picture of that in the next slide, and get about half a meter per day on average, which is really high SUD rates. Think about the thing about submarine groundwater discharge, it occurs over a massive spatial scale. So the fluxes can be low, but basically it's occurring over the entire bed of the Bay of Fundy, as well as the whole shoreline. So small fluxes times huge area can still be a lot of volumetric exchange. And then we had tidal signals again in the ocean, which I mentioned. And then these are two different tidal signals in the piezometers. The high tide one was, our logger was dry most of the time, so we had to use this mid tide one. But you can use Darcy's law. If you know how the tidal signals go up into the aquifer, you can get hydraulic properties. And then if you know the horizontal gradient, you can multiply by K to get Darcy flux, which is sort of on the same order of magnitude, although there's lots of uncertainty, as is always the case in hydrogeology. So this is us collecting the bag from this seepage meter here. This is after just one tidal cycle. I've done a bunch of these seepage meter tests other places, and we use this little cylinder that we usually fill up like 1/10 of the way and measure the volume. But here we get these bags, take two of us to lift, and that graduated cylinder was pretty useless. So we were just dumping them into buckets and counting the number of buckets that it filled. And I do think our seepage meter samples are probably biased to the low end because the bags are filling up over the tidal cycle. Here's the activities of radium 224 and 228. And basically this is a surface water tide here corresponding to the right axis, and is always the case for anything that's enriched in groundwater. There's groundwater flowing to the ocean. If there's some constituent enriched in groundwater, it'll have the highest concentration at low tide because the gradient's highest. That's the most groundwater is coming out at low tide, but also there's the least amount of surface water for mixing. So that's true of nitrate around the coast or lots of other things. This is our boat measurements for radium 224, which is a shorter half-life one. And here's our shoreline measurements. And again, they're out of phase with the tide, which is normal. And then the longer half-life radium 228, again, out of phase with the tide in both locations. But you can do mixing models for this sort of thing and get average SGD rates that are over scales that are more useful than a single seepage meter. So getting SGD rates sort of on the same order of magnitude, less than a meter per day, but getting pretty close. So here's all our measurements together. Red are the shoreline ones, blue are the offshore ones. And again, this probably looks bad for a lot of people, but it's actually really close estimates for the different measurements. And considering we're always dealing with like an order of magnitude uncertainty in hydrogeology with K estimates. And this is work by, really Aaron Mohammed did most of it, but he didn't want to write it, so a master student wrote it. Instead, Ray Craddock. So megatidal conditions along the Bay of Fundy or hypertidal conditions drive the circulation of groundwater and surface water. So just because we see things happening at the surface doesn't mean that's the only place things are happening. And in the context of sea level rise and also higher tidal ranges, that's something I haven't talked about, but with sea level rise, the period of the basin gets closer to the M2 tidal constituents, you actually get a higher tidal signal with sea level rise as well because of tidal resonance effects. So all of these will drive saltwater intrusion, whether that's movement of the deeper salt wedge or it's movement of the upper saline plume, or it's just more vertical flooding. I think I've shown examples of all that. And that can also drive potentially more submarine groundwater discharge. And I guess I didn't really talk about why that matters, but submarine groundwater discharge tends to have a very different chemistry than the coastal ocean. So it has a big role in terms of the biogeochemistry of an area, especially poorly mixed areas. So probably not so important in the Bay of Fundy. We just studied it here because we thought we'd find some of the highest SGD rates in the world, which we did. And so when people are thinking about decisions about dike, they should be thinking about what happens to groundwater as well. And that's sort of more natural and agricultural landscape. So we wrote this little comment this summer on the fact that in urban settings, when people are thinking about climate change in cities, which is a new IPCC special report coming out on this, that they need to think about the changes to groundwater along the coast as well. So it's not just coastal flooding, but it's also groundwater flooding, which can really impact. Well, that's basically sea level rise driven groundwater flooding. You can have deeper wedge movement, you can have vertical flooding, you can have saltwater intrusion, not just into fresh groundwater, but you can have it going into concrete, for example, and having issues with rebar reinforcement or pipes. So corrosion problems. All right, I promised to finish with some connecting this back to coastal geotechnics. And to do that, I want to draw your attention to this WIRE's water review article, which I had no part of, but I thought was a really cool article. And it basically, the whole article is about how tidal signals go into groundwater systems. And hydrogeologists have been thinking about this a long time. It seems like a niche topic, but they've been working on it since the 50s. And in the world of groundwater science and engineering, we perturb aquifers all the time to get hydraulic properties. So what we call pumping tests or pump tests, where we pump groundwater out of one well, look at how the nearby wells respond to try to get the aquifer properties that we need for design, like hydraulic connectivity, transmissivity, storage. And here's sort of the classic equation. It's just a solution to a hydraulic diffusion equation, 1D hydraulic diffusion. The solution looks the exact same as the solution to heat diffusion or solute diffusion when you have a periodic boundary condition. So this h of xt, it's the head in the groundwater system as a function of distance from the ocean and time. It depends on the ocean tidal amplitude. It depends on a damping factor, which depends on the distance you are inland as well as properties of the aquifer. And then you also have a lagging factor, so you have a phase shift in your groundwater tidal signal relative to your ocean tide. And both the damping factor and the lagging factor depend on something called hydraulic diffusivity, which is the ratio of transmissivity, T, which is hydraulic connectivity times vertical thickness. It's the ratio of that to storativity, S, which is the storage coefficient. All right, so this paper I mentioned shows all these different types of aquifers, which have different properties and different storage, and sometimes they're multi-layered systems. This year, book by my colleagues, Jimmy and Vincent's really cool chapter on tidal signal propagation. But the point is, I think a lot of people think about transmissivity when they're hydrogeologists, and I think coastal geotech people, they think about K as well, but often think about properties that relate to the storage coefficient, which isn't always called the same thing across the disciplines. So again, two types of aquifers that are important to think about, and I brought this up in the tidal signal propagation point earlier. So unconfined aquifers have this water table that goes up and down. So the storage effects in an unconfined aquifer, which is usually the top aquifer, comes from the actual water table moving up and down. So it's dewatering or rewatering. So that's really a function of the porosity, the drainable porosity. So the storage coefficient S in an unconfined aquifer is specifically called specific yield. That only applies for unconfined aquifers. Some people call them phreatic aquifers or water table aquifers, the ones that have a water table in them that moves up and down. But most people actually pump from confined aquifers, which are overlain by a confining unit, a low permeability aquitard or something. And those do not dewater, they don't drain or become dry. They release water when you pump them by basically the aquifer squishing together, which is why we have consolidation or those sorts of effects that geotech people study. And so the relative storage term, S, storativity, or sometimes called storage coefficient, is a function of the specific storage times the thickness. So basically it matters how thick the layer is, how much it's going to squish, as you would all know. So specific storage is specifically defined as the volume of water released per unit area of a confined aquifer per unit drop in head. And if you go to the equation on the top, it depends on the water density and the gravity, but mostly it depends on these compressibility terms. Beta is the compressibility of water, alpha is the compressibility of the matrix. So not individual grains, but how they're sort of structured and connected together. So very similar concepts, I think, to CV used in geotechnical engineering. Things get really tricky though when things are tidally inundated. And the reason that that's a problem, especially in a place like the Bay of Fundy where you might be inundated by meters of water, is that the total stress starts changing. So in hydrogeology, total stress is usually assumed to be constant. So if we pump from an aquifer, the pore water pressure is dropped, but the effective stress goes up by the same amount, just opposite direction. That's how groundwater models work. And that's how all the analytical solutions that are used for tidal signal propagation to back out groundwater properties or aquifer properties, that's how they work. So if we're trying to work in something like a salt marsh, which gets tidally inundated, or a tidal mudflat along the Bay of Fundy, we actually have to hack our groundwater models to try to deal with the storage term in a different way. So we don't assume this reciprocal relationship between pore water pressure and effective stress. Basically, we don't assume total stress is constant. And so I think there's probably a lot of work at a coastal geotech or geomechanical models that could help us deal with that better. And so to kind of get at this, I started working with Kurylyk on this. He's really a good friend of mine, a really nice guy. And Nina, I think, spent a bit of time working with him when she was at Dalhousie. He's the background more in geo-environmental work, but he's interested in dikes. He grew up in Windsor, which is a dike town. And he put in these vibrating wire piezometers with his student, Peter Roswell, and tried to study pore water pressures in front of this dike. What he's interested in is if you build these dikes up, you can generate this like excess pore water pressure that needs to drain out. And so trying to understand how that could work based on the properties of these systems is interesting. I don't think I've mentioned this already, but one of the nice things about tidal signal propagation to back out properties is that it works on scales that are kind of useful for design. So if you take a sample back to the lab, you get a point measurement, but if you do tidal signal propagation, maybe you get estimates that are relevant on meters, tens of meters, some cases hundreds of meters. So you get average properties over spatial scales that are useful. And these are some of the pore water pressure signals that Peter collected in these piezometers. And I don't want to go into this great deal. This is really Craig's work, not mine, but just to make the point that we use models like Rock Science, I think it's called Geotech World, but also CW, which I'm a bit more familiar with because it's a Canadian model, and show that when you try to just simulate hydraulic diffusion, which is that celerity effect of pressure signals going in, you cannot reproduce the high sine wave pressure responses that we see pore water pressure. The only way that can work is actually applying changes to total stress along the surface, which is probably obvious to coastal geotech people, but hydrogeologists don't do that. Another cool paper that I think connects these themes together a lot just came out in Geophysical Research Letters, which is where I do most of my service work, I guess, for journals, and so I tend to see the papers a bit more. And this is in China. Again, I didn't do this study, wasn't involved at all, but I just thought it was cool. They put fiber optic systems into these piezometers to monitor. Well, put fiber optic systems in the boreholes to monitor strain, and had vibrating wire piezometers installed. And they had a pretty deep borehole, several tens of meters, like up to 80 meters. And basically, they're trying to get the deformation modulus for linking stress and strain, which is useful for seismic analysis, landslides, other sort of geotech applications. And here's some of the cool data. Again, the stressor on this system is the tide, so they're not actually perturbing it any other way. They're using what we call in environmental science world an environmental tracer, so a natural perturbation to the system, look at the natural system response to the natural perturbation and try to back out aquifer, or in this case, not aquifer properties, but subsurface properties. And so you see these plots they have of pore water pressure changes versus strain, and trying to get at stiffness of this material to several tens of meters, which I thought was really cool work. So just to make the point that regardless of what environment you're working in, and certainly the focus of this project, I understand, is in tidal mudflats, but the tidal signal propagation down into like mudflat sediment or into aquifers at different spatial scales, depending on the K, can tell you a lot about those systems and how they work on their properties. And I actually think we could do a lot better job as a community in tying together the work in coastal hydrogeology and coastal geotechnics. It's pretty connected, and sort of thinking about that in my head. At some point, I'm going to write something. I'm not sure when. And there's a really cool book that I think is used more in hydrogeology, but it's kind of cool tying together some of the ideas. And I think we can learn a lot if we work together. I started doing this work with geotechnical engineering in general when I got into permafrost, and nobody had really done work on permafrost in hydrogeology, or very few had, but people have been doing it as geotech engineers for decades, and I realized a lot of the questions I thought I was solving had already been solved. Thank you to funding, and that's it.
Thank you so much for this great presentation. And so we do have some time for questions. And typically we start here in the room to give people online the chance to get their hands up. So do we have a question here in the room?
So I know you mentioned like kind of midway through the presentation that like after that dike was brought down, you started seeing like residual values in the sediment about like 5,000 microsiemens. Were those like at zero previously, or were they sitting kind of at like
really close to zero? Yeah.
Okay.
Except at great depth, because I think we would see some higher salinity deeper, or higher EC. And I think it had to do with the fact that has been diked for hundreds of years, but at some point in the past, it used to be tidally inundated before they put the dike in. over sort of 100-year timescales, that those effects are still present, which is really cool too, I think.
Yeah, that's really interesting. Thank you.
For the people online, if you have a question, please put your hand up or put it in the chat. Any other questions here?
Mhm.
Do you usually incorporate pore pressure measurements in your research, or is that?
So probably not in the way that you do, only if we're measuring them in piezometers or wells, but not like bearing RBR lockers, which I think you guys do, which I think is very cool. I actually got some people doing that this past summer, but I need to think a little bit more, because when you're looking at like shorter period wind waves, but like swell going into beach sediment, for example, that you probably all understand this better than me, but the piezometer damps a lot of those effects out. So unless you're like burying it, you'd miss it. So I'm trying to think. I think that's what your abstract's about, if I remember a little bit.
Yeah.
That's cool. I look forward to it.
We have a question from Emily. Emily, do you want to unmute yourself?
Sure. I was just really interested in your time series plot of the 2 different radium isotope activities with the tidal cycles. How do you measure it at such high temporal frequency?
That's a good question. I wasn't on the boat with them, but they basically, you collect the samples and see where was that? Trying to think of where I am here. You collect the samples and analyze it later in the lab. So collecting it's not that challenging at that frequency, but the trick is getting them to a lab for these shorter half-life isotopes. And we didn't have any set up really good at Dalhousie for doing this, so we airmailed them quickly down to, well, in our position, they're down to Joe at Old Dominion University. But there's a system called the RADIC that Ralph Arnold's built. I don't know if you have a lot of expertise in this, maybe far more than me, but that's the system that they analyze. So they basically they run the pore water, they pump it through fibers and then collect the fibers and analyze them in the lab through this RADIC system, which can take a long time, I think.
Yeah, no kidding. What volume of water did you have to collect for that?
Yeah, that's a good question. For each sample, I think there are probably in the order of tens of liters that are run through the fiber. But there's like the more you run through, the better, I think. But if you're trying to collect measurements on like hourly time scales, it gets tricky. But I can't remember right offhand, because basically we had like a pump set up and it was running through. These fibers are in like a tube and you're running the water through the fibers and through the tube and then collecting them after the fact. And I was not doing any of that. And I'm not a geochemist, so I can't remember offhand. But I know that they were running pretty close to the full time, I think, between each sample. So I think it would be at least tens of liters going through.
Gotcha.
It's pretty slow.
Yeah, that sounds like a lot of work. Thank you.
Yeah.
Great. Thanks, Emily. Any other questions here in the room, online?
I have one, I guess.
Yeah.
I'm curious about, like, and thinking about how much the community is affected by the saltwater intrusion. I mean, surely they talk about it and have meetings about it and stuff. How much of your work has been like shared with them, or do you feel like it's too early for that? Or I'm just curious what your interactions are with the people that live there.
I think so. We do have a bigger project, at least bigger in terms of funding, that's very community oriented. So we have workshops in communities on saltwater intrusion. I have not been convinced those have been fruitful workshops. A lot of saltwater intrusion problems to date in Nova Scotia are just really improper decisions about well placement and pumping rates as opposed to sea level rise driven. I think they're just starting to see the effects of sea level rise driven saltwater intrusion in some communities, but a lot of cases where they've actually had to relocate wells just because they were like pumping way too high a rate where they're at, as opposed to like places around Florida where you have like obviously more extensive flooding from hurricanes. Like Cedar Keys is an area where maybe they'd over pumped some there, but I also think that vertical saltwater intrusion is probably a big problem in low elevation areas of Florida. In Nova Scotia, as Nina would know, there tends to be big bluffs along most of the coastline, and people aren't pumping from really low elevation locations. So that's not to say saltwater intrusion is not a problem. I think it is like climate change driven, but I think the amount that's experienced so far has primarily been poor decisions by municipalities or homeowners. Not necessarily poor. I can't blame someone for not understanding a system, but it was decision based. Like, for example, just a few days ago, some people I know bought a house and the driller drilled super deep and brought up. So that salt wedge just goes in deep. So the deeper you drill, the more likely you are to hit a salt wedge, even though some people keep trying to drill away from salt water. And they brought it at a higher head. So the salt water came all up the uncased borehole and contaminated like the whole aquifer where everyone else was pumping. So everyone's wells were really, it's like a few days ago. It's pretty devastating. I shouldn't laugh, but yeah, these sorts of things happen a lot. Bad decision making.
Any other questions? I had a question. So I know that in the Bay of Fundy, some of the flats are pretty sandy and you can easily walk on,
Yeah,
and then you are suddenly stepping into them where it's like, okay, I get stuck here, right? With the dikes, I was wondering if the dikes if you observed any certain sediment types that tend to accumulate more in front of the dikes, because I think they reroute water, right? So I was wondering if there's any observation on that.
That's probably a good observation. I think I have observed that anecdotally, like just we can usually make your way around closer to the dikes a lot easier. And as soon as you go a few hundreds of meters, it's pretty different. But I hadn't really connected those like you have there. That's interesting. I'll have to think about that more.
Any other last question? Online, last chance? No? Okay. Thank you very much again for this great presentation. I appreciate it. Thanks everyone for tuning in online and people for being here, and stay on the lookout for our next Bioflat seminar in the new year. We don't have really a date or a topic yet, but I think we will probably figure that out very soon. So thanks everyone for joining. Have a good rest of your day. Bye-bye.
Need to